The deep silence of the night sky. The Milky Way stretches across the darkness like a river of fire. Billions of stars burn with quiet defiance, drifting in orbits carved long before the first spark of life flickered on Earth. To the eye, it appears eternal, a serene wheel of light turning endlessly in the void. Yet beneath this grace lies a hidden truth. Every star, every drifting cloud of gas, every world circling far-off suns is caught in a dance it cannot escape. A choreography dictated by something unseen. At the very heart of our galaxy lies an absence, a hollow core where light itself cannot remain. Astronomers call it Sagittarius A. It is not a star, not a cluster, not even matter in any form we can touch. It is an invisible force, a well of gravity so absolute that time bends, and space itself folds around it. Though it has no light of its own, its power is written into the motion of the heavens. Stars orbit it like moths around a flame they can never reach, their paths betraying the presence of a master hidden in the dark. This presence is both creator and destroyer. It devours with silence, swallowing anything that dares to wander too close, and yet, without it, the Milky Way would unravel, its spiral arms drifting into the void, its stars scattering into aimless exile. The paradox is haunting. At the heart of beauty lies a monster. At the center of order, chaos itself. Our galaxy breathes, holds its shape, and endures only because of this shadow. An anchor of darkness, invisible to human eyes, controls everything. We know. This is the story of Sagittarius A, the invisible force that rules the Milky Way, under the veil of night. Long before the language of galaxies or the mathematics of space-time, humanity looked upward and wondered what shape the universe truly held. The Milky Way spilled across the heavens like a pale, ghostly bridge, a river of stars that seemed to divide the sky into two halves. Ancient cultures gave it names steeped in myth: the path of souls, the backbone of the cosmos, the scar left by the gods. Yet for all its majesty, no one could have imagined that this shimmering band concealed within it a secret more powerful than any myth could capture. By the 17th century, as telescopes brought the distant closer, the work of mapping this river of light began. Astronomers like William Herschel, guided by curiosity and primitive instruments, sought to chart the Milky Way's stars. Through painstaking catalogues, they attempted to reconstruct the structure of the galaxy from their small island of Earth. But their vision was limited by what human eyes could see: a galaxy imagined as a disk with the sun near its center. A comforting thought that placed humanity at the heart of creation. Herschel's maps were remarkable for their time, yet incomplete, blinded by the dense clouds of gas and dust that veiled the galaxy's true core. The truth was far more distant and far darker. In the 1930s, a new kind of astronomy began to listen to the universe rather than simply look at it. Radio waves, long and unbroken by dust, could pass through the galactic fog. In 1932, engineer Carl Jansky detected an unusual hiss from the sky while studying static for radio communications. Its origin traced not to earthly interference, but to the very heart of the Milky Way. The center of the galaxy was whispering in frequencies no eye could see. As radio astronomy matured through the mid-20th century, the whispers became clearer. Astronomers discovered that the constellation Sagittarius pointed directly toward the galactic core, where an intense, compact source of radio emissions burned invisibly. By the early 1970s, this region was named Sagittarius A, a place that radiated with immense energy, yet showed no visible star. Observers were struck by its strangeness. Something powerful lay hidden behind the dust, something compact enough to fit within the orbit of planets, yet luminous in radio frequencies that pierced the darkness. At first, explanations stumbled. Perhaps it was a dense cluster of young stars, their energies combining into a furious signal. Or perhaps a rare stellar remnant, a collapsed core brighter than expected. But every hypothesis seemed too weak, too fragile, to account for the sheer force contained within this mysterious beacon. It was a clue left half buried in the dust. The suggestion that the galaxy's center was not a place of shining radiance, but of invisible gravity, a darkness whose presence could only be measured by the light it distorted and the waves it cast outward. The origins of its discovery were humble, almost accidental, and yet, from these first glimpses, humanity stood on the edge of realizing that at the heart of the Milky Way there was not light, but shadow. The discovery of Sagittarius A as a strange, compact radio source ignited both fascination and unease in the scientific community. For centuries, astronomy had been a study of light, stars, nebulae, galaxies, all luminous, all radiant. The cosmos had always been defined by brightness, by what the eye could see or the telescope could reveal. But here was something different. A source at the very center of the galaxy, invisible to optical instruments, yet releasing powerful radio signals as if speaking in a language beyond human sight. The idea unsettled astronomers. If the heart of the Milky Way was hidden, what else might lurk there? Initial interpretations leaned toward caution. Many believed Sagittarius A was no more than a tightly packed cluster of stars, so dense that their combined radiation appeared as a single source. This explanation fit comfortably within existing frameworks of stellar astronomy. But even in its early days, the evidence hinted that something more profound was at play. The measurements suggested that the region emitting the radio waves was extraordinarily compact, too compact for ordinary stellar systems. Theories of neutron stars, stellar remnants compressed into spheres no larger than a city, were considered. Yet the energy output seemed far too large for a neutron star alone, and no known object fit the description entirely. Here, Einstein's general theory of relativity loomed in the background. Published in 1915, it had predicted the possibility of black holes, regions of space-time so warped by gravity that not even light could escape. But even Einstein himself doubted such entities would ever manifest in nature. For decades, black holes remained more of a mathematical curiosity than a physical reality. The suggestion that one could exist at the very center of our galaxy was not just bold, it bordered on the unthinkable. To accept it meant that the Milky Way itself was bound together by a force born not of creation, but of collapse. Scientists debated fiercely. To some, Sagittarius A offered a thrilling possibility, proof that black holes were not merely equations, but cosmic realities. To others, it represented a leap too far, an attempt to explain the unknown with speculation rather than evidence. The 1960s and 70s were already a fertile period for astrophysics, with quasars distant, energetic beacons being identified as powered by supermassive black holes. Could Sagittarius A be the same? Could our own galaxy harbor such an object? At its core, the parallels were difficult to ignore, yet direct evidence remained elusive. The cultural imagination seized on the idea quickly. Newspapers and magazines described black holes as cosmic monsters or gravity traps, invisible devourers waiting in the dark. For the public, the thought that the Milky Way was ruled by such a presence blurred the line between science and myth. But for astronomers, the mystery demanded patience, precision, and decades of observation. They knew that if Sagittarius A truly concealed a black hole, the stars themselves would betray its presence, orbiting in ways that could not be explained. Otherwise, thus began a new chapter in astronomy, one that demanded not just instruments, but endurance. For if the galaxy's hidden heart was indeed a black hole, it would take generations of starlight, measured carefully, to prove it. And so the suspicion hardened into a challenge, to look into the dust-shrouded center of the Milky Way and reveal whether the most terrifying prediction of relativity was not only real, but central to everything we are. When Sagittarius A was first recognized as a compact and luminous radio source, the reactions were hesitant, even divided. To most astronomers of the mid-20th century, the suggestion that the very heart of the Milky Way could be occupied by a black hole was too extreme, too unsettling to accept without overwhelming evidence. For centuries, the cosmos had been imagined as a theater of stars, their light defining the very essence of astronomy. To propose that the central engine of our galaxy was not a beacon of radiance, but a pit of darkness, ran against intuition, against comfort, against the tradition of celestial order. The first explanations clung to the familiar. Many suggested that Sagittarius A might be nothing more than a dense concentration of stars, their combined gravity producing the strange effects, and their collective radiation mimicking the energy of a single, extraordinary source. Others imagined clusters of neutron stars, stellar corpses, compressed into unimaginable densities, huddled together at the center, their presence masked by the dust that veils the galactic core from view. These models allowed scientists to preserve a picture of the Milky Way in which light, even the dying embers of stars, still ruled its center. Yet, almost from the beginning, the numbers strained belief. Measurements of stellar motions, though primitive, hinted at an invisible mass millions of times greater than the Sun, all confined to a region scarcely larger than the solar system. Such density defied the possibilities of ordinary matter. Even neutron stars, exotic as they were, could not be packed in such numbers without collapsing into something deeper. Quietly, the predictions of general relativity returned to the conversation. Einstein's equations, long respected but often regarded as abstract, had suggested that under the right conditions, matter could collapse into a singularity, forming a region from which nothing, not even light, could escape for decades. These objects were theoretical phantoms, mathematical curiosities more than physical realities. Einstein himself doubted nature would permit them. And yet, here in the core of the Milky Way, the possibility began to press against the boundaries of denial. The scientific community fractured into camps. Some embraced the bold idea of a supermassive black hole, aligning Sagittarius A with the mysterious quasars newly observed at the edges of the universe. These distant, brilliant engines seemed to shine with the fury of black holes feeding on surrounding matter, their existence hinting that such titans might not be rare. If quasars could blaze in the young universe, could not a quieter, dormant black hole slumber at the heart of our own galaxy? Others resisted, holding firmly to star cluster explanations or proposing new, exotic states of matter that might mimic the effects without invoking the frightening finality of a singularity. Outside the halls of academia, the notion spread quickly. Newspapers, magazines, and broadcasts seized on the phrase black hole with a fascination bordering on obsession. Here was a concept that married the rigor of science with the drama of myth, an invisible monster at the heart of everything, unseen yet inescapable. The public imagination is filled with visions of cosmic drains swallowing stars, of galaxies, governed by unseen predators. In a world entering the space age, still adjusting to the sight of Earth as a fragile sphere floating in darkness, the revelation that the Milky Way itself was anchored by something so violent struck a chord of both fear and awe. Philosophically, the implications were profound. Humanity had long taken comfort in the idea of a radiant core, of a galaxy illuminated from within by some great stellar congregation. To discover instead that the Milky Way's balance depended on darkness, that its spiral arms circled not a source of light but a void of unimaginable gravity, was a shock that unsettled even seasoned scientists. It suggested that creation and destruction were not opposites in the universe, but partners, that the very structure of our home galaxy was bound to an entity defined not by presence, but by absence. The skepticism lingered, but so too did the questions. If this was not a star cluster, then what could compress millions of suns into the space of a single star's orbit? If it was not a neutron star, then what kind of object could survive with such density and power? Each new observation added weight to the mystery, pushing explanations toward a threshold that many were reluctant to cross. Somewhere within the dust and gas of Sagittarius, something extraordinary was hiding. The galaxy's greatest secret was not its radiant stars, but its invisible center, a discovery that would soon force science to confront the very edges of what it believed possible. The skepticism that defined the early years of Sagittarius A gradually gave way to determination. If theories alone could not settle the question, then the evidence would have to be found in the movements of the stars themselves. The galactic center, hidden behind vast curtains of interstellar dust, demanded a new kind of vision. Ordinary telescopes, which relied on visible light, were blind to the heart of the Milky Way. What was needed was a way to pierce through the darkness, to observe the faint glimmers of starlight that managed to escape the obscuring shrouds of gas and dust. Infrared astronomy became the tool of choice, allowing astronomers to look deeper into the core than ever before. By the late 20th century, two groups emerged at the forefront of this search, one led by Reinhard Genzel in Europe, and another by Andrea Ghez in the United States. Each worked independently, driven by the same vision to chart the orbits of stars, so close to the galactic center that their paths would betray the nature of the hidden force guiding them. These stars, later called diastars, moved with extraordinary speeds, whipping around the core in dizzying orbits that could only be explained by the pull of something immensely massive and invisible. But the task was monumental. These were not planets circling a nearby sun, easy to track within a human lifetime. These were stars orbiting an unseen anchor 26,000 light-years away, their motions subtle, requiring the patience of decades to measure, with adaptive optics, correcting the distortions of Earth's atmosphere. Observatories in Hawaii and Chile began to record their dance. Year after year, images accumulated, each faint point of light charted against the invisible backdrop of Sagittarius A. Slowly, patterns began to emerge. Some stars traced elongated loops, taking centuries to complete a single orbit. Others raced so quickly that their paths shifted within mere decades, offering precious glimpses of their curves around the unseen core. Among them was one star in particular, known as S2, whose orbit would become the defining proof of the invisible force. At the galaxy's center, the effort was painstaking, requiring the dedication of entire careers. Astronomers returned to the same stars night after night, year after year, gathering fragments of their journeys through space. Each observation was like a brushstroke on an unfinished canvas, building toward a picture that could confirm or shatter. The idea of a supermassive black hole. For some, it was a test of patience as much as science. Unlike laboratory experiments that yield results in days or months, the proof of Sagittarius A demanded time measured in decades. It was a scientific wager made not just by individuals, but by generations. Yet even as the data accumulated, the mystery deepened. The stars moved too fast, too close to an invisible center, their paths suggesting a gravitational pull stronger than any known cluster of ordinary matter could provide. The alternative explanations, dense star groups, clouds of exotic particles, hidden neutron stars began to collapse under the weight of observation. The evidence was aligning toward a conclusion many had resisted. At the very core of the Milky Way, something existed that could not be explained away by ordinary astrophysics. Still, the final step had not yet been taken. Observing a handful of stars was not enough. What was required was precision, the ability to trace entire orbits, to measure not just speed but the invisible hand guiding them. Only then could the galaxy's secret be revealed in full. And so the long vigil continued, astronomers watching. Stars circle in absence, hoping that their paths would one day expose the truth of the monster hidden at the heart of everything. The veil that had long concealed the heart of the Milky Way was not impenetrable, only stubborn. Ordinary starlight faltered against the dense clouds of dust and gas, vanishing before it could ever escape to Earth's telescopes. But light has many forms, and some could slip between the particles that obscured the galaxy's center. In the closing decades of the 20th century, astronomers turned to infrared wavelengths, able to pierce through the shroud and reveal what had remained hidden for centuries. It was like watching shadows dissolve, the outlines of long-lost figures emerging on a stage that had always been there, silent but waiting. High atop Mauna Kea in Hawaii, and later from the high deserts of Chile, new instruments strained against the limits of precision. Adaptive optics, correcting the distortions of Earth's atmosphere, sharpened the view to an unprecedented clarity. For the first time, astronomers could track the faint, flickering lights of individual stars embedded in the galactic core. These stars were not drifting slowly in a serene celestial ballet. They were racing, whipping around some invisible anchor, with speeds so astonishing they defied ordinary explanation. It was here that two parallel quests began, separated by continents but united by the same mystery. Reinhard Genzel in Europe and Andrea Ghez in the United States both directed their efforts toward charting the motions of these central stars. Their work became a study not of light, but of movement. Each point of light captured on photographic plates or digital sensors was a clue, a fragment of an orbit traced across the abyss of time. The task demanded patience that stretched beyond the boundaries of a single experiment, requiring not days or months, but decades of careful measurement. Among these stars, one group would become legendary, the S. They were young, massive, and impossibly close to the hidden force at the galaxy's core. Their orbits were wild, bending sharply around an unseen center, their velocities soaring to thousands of kilometers per second. No ordinary cluster of stars could generate such gravitational power. No dense knot of matter could remain stable under such extreme conditions. The stars were behaving as though tethered by an object of unimaginable weight, compacted into a volume no larger than our solar system. The most important of these became known as S2. Its orbit, elongated and elegant, drew it perilously close to the invisible core every 16 years. Each return was an opportunity to measure not just its speed, but the space itself through which it traveled. As decades passed, astronomers watched S2's full journey unfold, tracing a path that could be compared directly to the predictions of Einstein's general relativity, and the results were unmistakable. Only a supermassive black hole, weighing more than 4 million suns, could explain the ferocity of its orbit. Still, the process was fragile. Atmospheric turbulence, instrumental limitations, even the sheer difficulty of observing stars so distant, all threatened to blur the truth. But the observations grew more precise, the data more consistent, the picture more undeniable. With every orbit measured, with every star tracked, the galaxy's hidden secret came into sharper focus. By the dawn of the new millennium, consensus was forming. The motions of the S-stars had ruled out alternative explanations. No dense cluster of neutron stars, no exotic ball of dark matter, no unknown mechanism could match the evidence. At the very center of the Milky Way, a singular presence exerted its silent dominance, not a radiant beacon, but a devouring shadow. A black hole of supermassive scale, the heart of our galaxy revealed at last. The turning point arrived with the close approach of the star S2 in the year 2002. For more than a decade, astronomers had been patiently recording its movements, slowly assembling a map of its long and perilous orbit. But this moment, when S2 swept inward and skimmed nearest to the galactic center, was different. It was as if the universe itself had orchestrated a grand unveiling, a stage on which the laws of nature could be tested under conditions never before observed. The star hurtled past the unseen core at speeds exceeding 7,500 kilometers per second, more than 25 million kilometers every hour. No ordinary gravitational source could account for such violence. With each observation, the data converged upon a singular truth: only a black hole of extraordinary mass could produce such acceleration without tearing the star apart. What made this passage even more remarkable was that it allowed astronomers to put Einstein's general relativity to its most extreme trial. As S2 approached closest to the hidden core, its light did not travel unaltered. Space itself curved under the immense weight of gravity, bending and stretching the path of photons as though the fabric of the cosmos were being pulled taut around an invisible stone. The wavelength of the stars, light shifted subtly but undeniably, stretched by the gravity it was escaping. This gravitational redshift, predicted a century earlier by Einstein, was at last measured with exquisite precision in the heart of the Milky Way. The star's orbit became not only evidence of mass, but of the very curvature of space and time. This was the breakthrough that ended decades of uncertainty. Rival theories crumbled under the weight of observation. A cluster of dark objects could not remain stable for long enough. A sphere of exotic particles could not reproduce the redshift so perfectly aligned with Einstein's equations. The simplest, most elegant explanation, and the only one consistent with the data, was that Sagittarius A was a supermassive black hole. 4 million suns compressed into a space smaller than the orbit of Mercury, wrapped in a veil from which no light could ever escape. The implications rippled outward. For centuries, humanity had imagined the heart of the galaxy as a radiant throne, a glowing source of cosmic order. Yet reality was stranger, more unsettling, and more profound. The Milky Way's stability was not upheld by a shining monarch, but by a shadow, a region of space-time where physics itself surrendered to mystery. The stars danced not around light, but around an absence. It was a revelation both terrifying and beautiful. The galaxy lives and breathes. Because of a darkness it can never illuminate. And with this realization came a deeper reflection. If the center of our own galaxy was governed by such a being, how many others must exist across the universe? Observations of distant galaxies hinted at the same truth. Supermassive black holes appeared to lurk at nearly every galactic core. They were not rare anomalies, but fundamental architects of cosmic structure. What once seemed like a cosmic aberration now appeared to be a universal law. Galaxies and black holes, bound together in a partnership as old as time itself. Sagittarius A was no longer just a radio source in the constellation of Sagittarius, nor merely a suspicion hidden behind dust and gas. It had become the most direct evidence that supermassive black holes were not myths of theory, but real, colossal entities shaping the very framework of the universe. The monster at the heart of the Milky Way was no longer invisible in theory. It was invisible in truth, yet undeniable in consequence. 2 decades of patience, precision, and devotion would culminate in one of the greatest revelations of modern astronomy. Year after year, winter after winter, astronomers pointed their instruments toward the center of the galaxy, capturing faint light from stars that seemed to orbit an emptiness. The painstaking work demanded endurance beyond individual lifetimes. A scientific relay passed between generations of researchers, yet the patience bore fruit. By tracing the elegant arcs of these stars, the most faithful of which was named S2, humanity began to sketch the invisible presence lurking in the dark. S2 became the key witness. Over 16 long years, its orbit carried it through a path both perilous and beautiful, swinging close to the galactic center before soaring outward again. When it returned for its closest approach in 2002, the mystery deepened into certainty. The star surged to breathtaking speed, traveling faster than 7,500 kilometers per second, a velocity impossible to sustain without an anchor of immense mass. The data left little room for doubt. Within the invisible point around which Esther circled lay the weight of 4 million suns, compressed into a space smaller than the orbit of Mercury. No cluster of faint stars could mimic such gravity. No exotic particle halo could endure such density. Only a black hole could remain. Sagittarius A was unmasked not by sight, but by the dance of stars held captive by its pull. The triumph of this realization was honored in 2020, when the Nobel Prize in Physics was awarded to Reinhard Genzel and Andrea Ghez, the 2 pioneers who had led rival teams in unraveling this cosmic mystery. Their decades of devotion had turned speculation into certainty, theory into proof. What Einstein had once imagined, and what skeptics had resisted, now stood as fact. The heart of the Milky Way was governed by a supermassive black hole, yet even this was not the end of the story. While infrared telescopes charted the movements of stars, radio astronomers dreamed of peering deeper still, of glimpsing the very edge of the abyss itself. This ambition gave birth to a project of unprecedented scope, the Event Horizon Telescope, a global network of observatories scattered across continents, synchronized to act as a single Earth-sized eye. By harnessing the technique of very long baseline interferometry, these telescopes stitched together their data, creating a resolution sharp enough to see what no instrument alone could capture. And then, in May of 2022, humanity's gaze fell at last upon the unseen. The Event Horizon Telescope unveiled the first direct image of Sagittarius A, not the black hole itself, for no light can ever escape its grasp, but its silhouette, a circular shadow, ringed by a halo of light bent and twisted by gravity's extremes. It was a portrait painted not in visible color, but in the warped glow of radio waves, a cosmic fingerprint carved into the fabric of space-time. The image was blurry, imperfect, and yet it carried a weight beyond measure. For the first time, humanity was no longer imagining the abyss. It was staring directly at its edge. That moment was more than a scientific milestone. It was a philosophical one. At the core of our galaxy, where myth and wonder once placed radiant deities, there stood instead a silent shadow, a void 1,000,000 times heavier than the sun, sculpting the destiny of stars and worlds. In that single image, the mystery of Sagittarius A was no longer abstract, no longer hidden. It was made real, and it was revealed as the true heart of the Milky Way, a heart of darkness, shaping light itself. The unveiling of Sagittarius A's shadow in 2022 did more than satisfy scientific curiosity. It marked a turning point in the human story, where imagination collided with evidence, and what had long been confined to equations and metaphor became a direct encounter with reality. For centuries, black holes were abstractions, ghosts, haunting the mathematics of general relativity, dismissed by many as impossible or absurd. Yet now, staring back at us from the galactic center, was the silent proof. The dark silhouette of Sagittarius A was not only a validation of Einstein's vision, but a profound reminder that the universe is stranger, heavier, and more enigmatic than even the boldest philosophies had once dared to suggest. In the faint, flickering halo of radio light, humanity caught its first glimpse of the abyss that defines its own home galaxy. The image itself, blurred and indistinct to the untrained eye, carried the weight of revelation because it revealed not the black hole directly, but the consequence of its gravity. Photons bent into a luminous ring. Space-time itself curved into a shape that could be captured by telescopes spread across the planet. This was more than a picture. It was a confrontation with scale. To look upon Sagittarius A was to look upon a gravitational well so deep that not even light could flee its boundaries, yet so vast that entire solar systems could disappear inside it. The numbers stagger the imagination. For million solar masses, contained within a region no larger than the orbit of Mercury, a cosmic titan compressed into an impossible silence, holding the galaxy together, unseen until now. But beyond the technical triumph, the moment rippled with a deeper, almost spiritual weight. For as the image circled the globe, it was no longer the exclusive domain of astronomers and physicists. Schoolchildren, poets, philosophers, and ordinary dreamers saw the glowing ring and felt the pull of something greater than themselves. The media spoke of it as a window into oblivion, as if humanity had pressed its face against the glass of the infinite. For some, it was exhilarating. For others, unsettling. The revelation that the very center of the Milky Way, the anchor around which billions of stars revolve, is not a beacon of creation, but a devourer of light, forced a re-evaluation of our cosmic story. The heart of our galaxy is not radiant, but shadowed, not a source of life, but an engine of disappearance. Yet there is beauty in this darkness. Black holes, once feared as destroyers, are now understood as sculptors of galaxies. Their gravity shapes the motion of stars. Their outbursts regulate the birth of new suns. Their hidden presence weaves order into the chaos of cosmic evolution. Sagittarius A, far from being a void of meaningless consumption, may be the silent conductor of the Milky Way's grand symphony. Without it, our galaxy might not exist in the form we know. In the shadow that so unsettles human imagination, there may also lie the stability that allowed Earth to form, oceans to flow, and minds to rise and wonder. The 2022 image was, in one sense, the end of a quest, the culmination of decades of observation, speculation, and perseverance. But in another sense, it was only the beginning. To capture the silhouette of Sagittarius A was to open a door, revealing mysteries yet deeper and more profound. How does matter behave on the edge of annihilation? What do the jets and flares from its accretion disk whisper about the physics of extreme spacetime? Could such abysses harbor pathways into realms unseen, bridges between universes, as some theories dare to propose? The shadow was not an answer, but an invitation, a reminder that knowledge often reveals more questions than it resolves. And so the story of Sagittarius A continues, expanding outward like ripples in a cosmic sea. What began as faint radio, static in the 1930s, had become, nearly a century later, the most intimate portrait of the abyss. It is a story of patience across generations, of human curiosity that refuses to yield to distance or obscurity. But above all, it is a story that asks us to look inward as much as outward. For in that dark silhouette, humanity sees not only the heart of the Milky Way, but a mirror of its own condition. Fragile beings orbiting the unknown, clinging to islands of light forever drawn toward questions that lie in shadow. At the heart of the Milky Way lies a paradox so vast it challenges the imagination. Sagittarius A, a cosmic anchor of 4 million solar masses, yet cloaked in silence. Its gravity binds hundreds of billions of stars into a galactic dance, but the question of its own origin lingers unresolved. Did this dark colossus emerge in the very infancy of the galaxy, a seed black hole collapsing from one of the first massive stars, growing fat on the debris of a chaotic early cosmos? Or did it form later, through the gradual merger of stellar corpses, compact remnants spiraling together until their combined weight tipped spacetime into collapse? In truth, no one yet knows. What is certain is that Sagittarius A has been here for billions of years, quietly sculpting the architecture of the Milky Way, its presence shaping the orbits of stars, the flow of gas, and perhaps even the destiny of worlds like Earth. Yet despite its current calm, evidence whispers of a more violent past. Vast structures discovered in 2010, twin lobes of gamma ray light towering above and below the galactic plane, revealed scars of ancient fury. These so-called Fermi bubbles extend nearly 25,000 light-years into space, dwarfing the galaxies. Disk, glowing with the aftershock of energies unleashed millions of years ago. What force could have carved such monumental shapes into the cosmos? Astronomers suspect they were the breath of Sagittarius A, a time when the black hole erupted in a storm of radiation and high-speed particles, an outburst powerful enough to reshape the galaxy's halo. Today, Sagittarius A is subdued, feeding only sporadically, producing faint X-ray flares as scraps of matter fall across its event horizon. But the Fermi bubbles stand as silent witnesses that this sleeping giant once roared, and may one day awaken again. This duality, dormant yet destructive, silent yet once violent, mirrors a broader truth about black holes. They are not merely destroyers as once imagined, but also paradoxical creators. In their feeding, they unleash winds and jets that compress clouds of interstellar gas, triggering the birth of new stars. Their gravity tears some stellar nurseries apart, while in other regions it ignites them into life. Near Sagittarius A, stars are found improbably close to the abyss. Their orbits tight and furious, their lives accelerated by the crushing tides of gravity. Some may one day be devoured whole, their energy flaring in a final burst before vanishing forever. Others are born in this chaotic crucible, young stars forged in defiance of the very forces that seek to unmake them. Creation and destruction, life and death play out side by side at the galactic center. A reminder that in the universe, endings and beginnings are often one and the same. The paradox grows deeper when considering its quiet today. Why, with so much matter swirling in the galactic core, does Sagittarius A consume so little? The Milky Way's central black hole is underfed compared to its cousins in active galaxies, where jets blaze for millions of light years. Perhaps gas is deflected by magnetic fields, or dispersed before it can reach the event horizon. Perhaps Sagittarius A is simply between feasts, biding its time. For now, it remains a gentle giant, its appetite restrained, while its history testifies that quiescence is only temporary in the life of such an object. What we call dormancy may only be the pause between catastrophes, and so the mystery deepens, not only of how Sagittarius A came to be, but of what role it truly plays in the evolution of the galaxy. It is both sculptor and destroyer, order and chaos entwined. Without it, the Milky Way might lack its structure. With it, stars are torn apart. In this paradox lies a reflection of the universe itself, a cosmos where creation emerges from violence, and beauty is born of catastrophe. The shadow at the center of our galaxy is not merely an abyss, but a mirror of the duality that shapes existence, a reminder that in the deepest darkness lies the very engine of light. Across the vast darkness of the cosmos, Sagittarius A serves, not only as the silent engine of the Milky Way, but as a window into the nature of all supermassive black holes. What has been uncovered here, in the quiet of our own galactic heart, reflects patterns observed in galaxies far more distant, luminous quasars, blazing active nuclei, and violent jets that stretch across intergalactic space. The difference is scale and timing, not nature. In the deep past, when the universe was young, supermassive black holes like Sagittarius A shone with a radiance that could outshine entire galaxies, their feeding frenzies painting the cosmos with torrents of energy. Today, ours is subdued, but its anatomy is the same. By observing the calm present, astronomers glimpse the echoes of a universal cycle of growth, eruption, and silence that defines the life of galaxies everywhere. The lessons drawn from Sagittarius A also stretch into the mystery of origins. Astronomers have found quasars powered by black holes, billions of solar masses heavy, already formed less than 1 billion years after the Big Bang. How could such titans grow so fast, in so little time? The question is sharpened by what is known about our own galactic core. Sagittarius A is massive, yet modest compared to those ancient giants. If it is the result of slow feeding over billions of years, then perhaps others were born differently, seeded by direct collapse of primordial gas clouds, bypassing the slow evolution of stars. Sagittarius A, in its restraint, may hold clues to why some black holes exploded into quasars, while others, like ours, remained quiet custodians of stellar families. The paradox of its silence becomes not a limitation, but a key to understanding why galaxies take such different paths. Yet its silence is not a guarantee of peace. In 2019, NASA's Chandra X-ray Observatory detected evidence that only a few centuries ago, Sagittarius A was far more active than it is today. Bright echoes of X-ray light, reflected from surrounding gas clouds, told of flares hundreds of times brighter than what is now seen. To humans, centuries seem like permanence. But for the galaxy, such timescales are the blink of an eye. The suggestion is clear. Sagittarius A may shift moods unpredictably, swinging from dormancy to violence, its appetite governed by the chaotic flow of matter drifting inward. A cloud of gas, a disrupted star, or a collision of molecular filaments may all be enough to awaken the monster, filling the center of the galaxy with a radiation storm that would echo for millennia. The deeper the investigation, the more profound the philosophical weight becomes. Sagittarius A embodies a cosmic paradox. It is an object defined by absence, a place where matter and light are lost forever, and yet its influence extends across 50,000 light-years, shaping the spiral arms of the galaxy and the lives of uncountable stars. It is invisible, yet it dictates structure on the grandest scales. To comprehend it is to confront a truth about the universe itself, that the forces which bind and preserve also consume and erase. In this way, Sagittarius A becomes more than an astronomical curiosity. It becomes a symbol of the balance that underlies existence, destruction braided into creation, silence masking violence, order arising from the abyss. For those who look into the galactic core, there is an unshakable sense of reflection. If Earth and the solar system are but one tiny fragment held within this spiral city of stars, then their very stability, their ability to harbor oceans, life, and thought, has been made possible by the presence of the darkness at the center. The abyss, indifferent and unseeing, has nonetheless cradled the galaxy, ensuring that orbits are maintained and structures endure. In its cold silence, Sagittarius A has been both executioner and guardian, both destroyer of stars and guarantor of cosmic order. Its story is not just the story of a black hole, but of how galaxies live, breathe, and persist at the very heart of the Milky Way. Sagittarius A is not merely a black hole. It is a crucible where the limits of human understanding are tested, a natural laboratory sculpted by gravity itself, where the laws written by Einstein a century ago are placed under the most unforgiving scrutiny the universe can provide. Here, within a few light hours of its shadow, matter is pushed to velocities and energies that no terrestrial experiment can hope to recreate. Light bends and time slows, warped into patterns that betray the hidden architecture of space-time. It is as though nature, in silence, has prepared a stage upon which the deepest questions of physics may be asked. The orbit of a single star, S2, became a turning point. Tracked for decades, its 16-year dance carried it perilously close to the abyss, whipping past Sagittarius A at nearly 3% the speed of light. When it swung through its closest approach in 2018, astronomers saw what Einstein predicted, and what no other environment could reveal with such clarity. The star's light stretched into red, not by motion alone, but by gravity itself. This gravitational redshift, the slowing of time's rhythm in the presence of extreme curvature, was measured with precision, a triumph that confirmed general relativity in yet another of its harshest tests. And yet, behind the triumph lay a deeper tension. If even the minutest deviation had been found, it might have signaled cracks in Einstein's century-old theory, cracks through which new physics could emerge. To many, the galactic center feels like a threshold, the mathematics of plasma spiraling into the event horizon, the entanglement of magnetic fields, the turbulence of inflowing gas, all remain only partly understood. Supercomputers attempt to model the chaos, but even their reconstructions are pale approximations of reality. The interplay between gravity, light, and matter near Sagittarius A is a symphony of extremes, where relativistic jets may form and dissolve, where magnetic storms twist through disks of incandescent plasma, and where time itself staggers toward stillness. In these dynamics, scientists glimpse not only the behaviors of matter, but the possibility of truths that theory has not yet caught. This is why Sagittarius A is often called a gateway, not in the literal sense of a passage into another world, but in its role as a portal of knowledge, where questions about the deepest structure of reality are pressed against the silence of the unknown. Some dream that, hidden in its shadow, clues to quantum gravity may be found, the long-sought union between Einstein's smooth spacetime and the grainy probabilities of the quantum world. Others speculate that phenomena so strange as wormholes or white holes might lurk behind the equations, theoretical cousins of black holes that could, in principle, lead to other regions of the universe or even to other universes altogether. The evidence remains elusive, but the possibility lingers, haunting and irresistible. Sagittarius A is, in this sense, a mirror. It reflects the limits of human understanding back upon itself, showing both the brilliance of what has been achieved and the vast gulf that remains. For now, it conforms to Einstein's vision, but every measurement, every image, every orbit traced around its unseen gravity carries within it the chance of something more, a whisper from the universe that the story is not complete. It is this tension, this quiet expectation at the frontier of knowledge, that makes the galactic core one of the most sacred laboratories in all of science. And so the galaxy's dark heart becomes not only an astronomical object, but a philosophical challenge, a riddle that stretches beyond the mathematics of relativity and into the very fabric of human inquiry. Each time a star like S brushes past Sagittarius A, it is as if the universe itself lifts a veil, granting a fleeting glimpse into the nature of reality. The gravitational redshift, measured in its light, is more than a technical confirmation. It is a reminder that time is not universal, that its rhythm bends under weight, that the ticking of the cosmic clock depends on where one stands in the curvature of space. Here, in this strange theater, what appears eternal is revealed as relative, fragile, and endlessly malleable. Yet the questions do not end with Einstein's success. For while general relativity describes the dance of stars and the bending of light with exquisite precision, it falters in the face of quantum mechanics. At the event horizon, where space-time collapses into silence, the two great pillars of physics stand in contradiction. Gravity demands a smooth continuum, while quantum theory insists on discreteness, on jittering fluctuations of energy and information. The black hole, then, is not only a graveyard of matter, but a battleground of ideas. Somewhere in its shadow lies the bridge between the infinitely large and the infinitesimally small, a bridge humanity has sought for a century, and still has not crossed, Astronomers and theorists often speak of Sagittarius A as a kind of cosmic laboratory, one constructed not by human hands, but by the universe itself. Plasma flows into its maw, magnetic fields twist in violent tangles, and particles accelerate to energies no earthly collider could ever achieve. In the glow of X and radio waves, researchers see turbulence and order interwoven, a dynamic portrait that is as beautiful as it is bewildering. Theoretical models struggle to keep pace, and simulations run on supercomputers attempt to capture the storm. Yet the reality at the galactic center is likely stranger than any ORITHM can yet conceive. The possibility that this black hole could harbor portals, wormholes connecting distant points in space-time, or white holes ejecting matter back into the cosmos, remains speculative but tantalizing. General relativity allows such solutions, though their stability and existence in nature are deeply uncertain. Still, the mere fact that the mathematics permits them hints at a universe richer than the imagination dares to picture. Could Sagittarius A be more than a silent anchor? Could it be a doorway, however unstable, into realms beyond perception? These are not fantasies, but genuine questions posed by physicists confronting the edges of their equations, where the fabric of reality frays. In 2022, when the Event Horizon Telescope revealed the first direct image of Sagittarius A's shadow, humanity's gaze fell upon this enigma with unprecedented intimacy. The golden ring of light, blurred yet unmistakable, encircled a void that seemed to stare back. But that image, powerful as it was, is not an end. It is a beginning. Future arrays, with sharper resolution and wider reach, may one day allow scientists to watch the chaos unfold in near real time, to see matter swirl, collapse, and vanish into darkness. Each new observation will carry with it the hope of discovery, of finding the subtle deviation that breaks Einstein's spell and guides science into a new paradigm. Sagittarius A is thus both an anchor and an opening. It anchors the stars, binding the Milky Way together through gravity's relentless pull. But it also opens the imagination, forcing humanity to confront the limits of knowledge and the haunting possibility that reality is far stranger than what is written in current laws. In its silence, it asks questions that science is still learning how to phrase. What is the true nature of time? Can information survive the fall into a singularity? Does space end at the horizon, or does it curve toward something beyond our comprehension? The answers remain hidden, cloaked in a darkness deeper than night. Yet the search continues, relentless, patient, and hopeful. For in the shadows of Sagittarius A, humanity finds not only the mystery of the cosmos, but the reflection of its own longing to know, to reach beyond what is seen, to uncover the hidden architecture of existence itself. At the heart of modern astrophysics lies a prevailing view, a framework forged from decades of careful observation and theory that seeks to explain the origins of Sagittarius A not as an anomaly, but as the natural consequence of cosmic history. In this telling, the black hole is not an accident, not a singular quirk of chance, but the expected end of a universal pattern, the silent anchor of a galaxy that was written into existence from its very birth, when the Milky Way emerged. From the primordial fog of the early universe, clouds of gas collapsed under their own gravity, giving rise to stars, clusters, and the first seeds of black holes. Over billions of years, through mergers of galaxies and the steady infall of matter, those seeds grew larger, consuming, colliding, and consolidating until what remained was a colossus, a black hole with a mass of 4 million suns dwelling. At the center of our spiral, the idea is known as hierarchical growth. Small structures merge to form larger ones. Star systems coalesce into galaxies, galaxies into clusters, and in their hearts, their darkest recesses, black holes merge as well. Each galactic collision may have carried in its core a central black hole, and when galaxies danced and merged, so too did these hidden titans. Their collisions shook space-time with waves of gravity, invisible to all but the most sensitive instruments, yet leaving behind a more massive remnant, the seed of the monster we now call Sagittarius A across cosmic time. This relentless process of merging and accretion wrote the script of the universe we observe today, where nearly every large galaxy carries a supermassive black hole in its heart. Matter did not simply fall into this abyss unchecked. Much of it spiraled inward through an accretion disk, a luminous maelstrom of gas heated to millions of degrees as it circled the event horizon. These disks are more than feeding grounds. They are engines of feedback, blasting energy outward in the form of radiation and winds. In the young Milky Way, such outflows may have sculpted the galaxy itself, preventing the collapse of all gas into stars, regulating starbirth in a delicate balance. This is the paradoxical role of black holes in galactic evolution. Though they consume, they also create. By heating, stirring, and redistributing matter, they prevent runaway collapse and enforce an equilibrium that allows galaxies to persist. Without such regulation, it is possible that galaxies like the Milky Way would look very different, smaller, denser, less ordered, and perhaps even less hospitable to life. Cosmic order, then, is not imposed from without, but arises from a cycle of chaos and control. The very presence of Sagittarius A may be what allows the Milky Way to retain its spiral arms, its regulated rhythms of starbirth and death. Black holes act as engines, not merely devourers. They shape the interstellar medium through feedback loops so vast they stretch across tens of thousands of light years. In the Milky Way, the clearest echo of this lies in the Fermi bubbles, twin structures of high-energy radiation rising far above and below the galactic plane, evidence of a past outburst when Sagittarius A burned brighter, sculpting its environment with unimaginable power. Underlying all of this is the unseen scaffolding of dark matter, an invisible halo that envelops the galaxy, outweighing ordinary matter by a factor of 5. Though its nature remains unknown, its gravitational pull is undeniable. It provides the framework upon which galaxies assemble and stabilize. Without it, the rapid motion of stars would tear the Milky Way apart. It is within this dark cocoon that Sagittarius A was able to take root and endure, its gravity harmonizing with the larger gravity of the halo. Both forces woven together in a cosmic dance that shapes not just one galaxy, but billions. From this perspective, Sagittarius A is no isolated mystery. It is a single piece in a vast universal puzzle. Every galaxy large enough to be luminous seems to carry a black hole in its center, and the mass of that black hole is often proportional to the size of the galaxy's central bulge of stars. This relationship, known as the M-sigma relation, suggests a profound connection. The growth of black holes and galaxies is inseparable, their destinies entangled across cosmic time. The Milky Way and Sagittarius A are simply one expression of a universal law, one echo of a pattern written into the architecture of the cosmos. Still, even within the mainstream view, mysteries remain. The precise timeline of Sagittarius A's growth is uncertain. Was it seeded by a stellar mass black hole in the earliest galaxies, patiently accreting matter for billions of years until it reached its present mass? Or did it begin larger, born from the direct collapse of a primordial gas cloud already massive in its infancy? Astronomers search for answers in the light of the most distant galaxies, peering across cosmic history to witness black holes that had already grown to billions of solar masses when the universe was less than 1 billion years old. These giants challenge even the mainstream models, suggesting that in some places, black holes grew far faster than expected. Sagittarius A, by contrast, appears modest, a restrained giant when compared to those early behemoths. Its quiet presence is not a failure of theory, but a reminder that black holes evolve in many ways, shaped by their environment, their feeding history, and the fates of the galaxies they inhabit. Thus, the mainstream view frames Sagittarius A not as an anomaly but as a chapter in the grand narrative of cosmic evolution. Its existence is not surprising, its mass not inexplicable. It is the natural outcome of a universe that builds from small to large, that regulates itself through cycles of consumption and creation, that grows complexity not in defiance of gravity, but because of it. The black hole is both destroyer and regulator, both singularity and system, both chaos and order. And in this dual role, it has helped make the Milky Way what it is today, a spiral galaxy alive with stars, planets, and the fragile spark of consciousness able, at last, to look inward and ask how it all began. Supercomputer simulations now allow scientists to recreate, in digital form, the processes that have unfolded across billions of years, testing whether the mainstream vision of hierarchical growth and black hole regulation truly matches the observed universe. These simulations, sometimes running for months on end, stitch together the physics of gravity, gas dynamics, magnetic fields, and dark matter into a single model, letting galaxies form and evolve before our eyes. In the simulated cosmos, galaxies collide and merge just as they do in reality. When they do, their central black holes spiral inward, radiating gravitational waves until they finally coalesce. What emerges is a heavier remnant, a black hole that grows stronger with each encounter. The result of these experiments is striking. Galaxies with supermassive black holes at their centers emerge as a natural product of cosmic evolution, not as rare accidents. Sagittarius A appears, in this light, not as an outlier but as an expected outcome, a quiet member of a vast family of galactic cores, each crowned by a dark heart. Observations from telescopes confirm these simulations. The Event Horizon Telescope revealed the shadow of the supermassive black hole at the center of M87, a galaxy far larger than the Milky Way. That shadow, a void rimmed by glowing plasma, proved that the same physics applies across scales. M87's black hole, more than 6 billion times the mass of the Sun, demonstrates the same structures of accretion, the same jets of matter flung outward at nearly the speed of light, as smaller black holes observed within our galaxy. The lesson is universal. Black holes grow with their galaxies, and galaxies evolve under their influence. Sagittarius A may seem small beside M87's colossal titan, but its role in the Milky Way is no less profound. Its outbursts have carved the halo of radiation we see as the Fermi bubbles. Its gravity sculpts the orbits of stars that skim dangerously close, whipping around at speeds that defy comprehension. The same rules apply everywhere. The details vary, but the pattern repeats. Evidence of this pattern deepens when astronomers measure the relationship between black hole mass and galactic bulge. Again and again, they find that the two quantities scale together. A galaxy's central stars and its hidden black hole grow in lockstep, as if tied by some invisible thread. This M-sigma relation suggests a fundamental law of nature, one that binds together the luminous and the dark. A black hole, born from collapse and destruction, somehow regulates the growth of the very stars that orbit it. Through powerful winds, radiation, and jets, it prevents uncontrolled collapse, enforcing a cosmic balance. Too much star formation, and the black hole ignites, driving gas outward. Too little, and the galaxy stagnates. In this balance lies the possibility of long-lived galactic structures, capable of hosting billions of worlds. The Milky Way itself is a beneficiary of this delicate feedback loop, one in which Sagittarius A has played a central, if largely invisible, role. In this view, black holes are not merely objects, but regulators, thermostats of the cosmos. They maintain the delicate conditions under which galaxies flourish. The paradox is profound. The most destructive forces in the universe, swallowing light and matter without end, are also the very engines that keep galaxies stable. Order emerges not in spite of destruction, but because of it. The collapse of matter into a singularity, the release of energy from an accretion disk, the explosive force of a jet. All of these processes ensure that galaxies like the Milky Way remain habitable for billions of years. Without such regulation, the cosmic stage might look far different. Galaxies collapsing into dense, chaotic knots of stars, or dissipating into featureless clouds, incapable of sustaining the fragile complexity we now call life. Dark matter, too, plays its silent part in this harmony. Its invisible halo enfolds the Milky Way, providing the gravitational foundation that stabilizes not only the stars, but the black hole itself. Without this hidden mass, the galaxy would not cohere its structure, unraveling under the rapid motions of its stars. It is in this unseen framework that Sagittarius A could grow safely, anchored in a gravitational sea that extends far beyond the reach of visible matter. Dark matter may be silent, but it is the quiet architect of the stage upon which galaxies and their black holes perform their eternal dance. In this sense, Sagittarius A is not only a child of stellar collapse and galactic mergers, but of the invisible cosmos itself, the hidden scaffolding of dark matter that gave it a home. The mainstream view, then, is one of profound unity. Sagittarius A is not an isolated anomaly, not a cosmic mistake, but part of a universal order that governs every massive galaxy. Its story is not only the Milky Way story, but a reflection of countless galaxies across the universe, each harboring its own dark heart. The lesson it offers is that destruction and creation are not opposites, but partners, entwined in cycles that sustain structure across billions of years. The black hole consumes, but by consuming it regulates. It collapses, but through collapse, it gives rise to order. It is both chaos and balance, both predator and gardener of the stars. In this paradox lies a truth as old as the universe itself, that creation is born from ruin, and that the darkest places in the cosmos are also the engines of its enduring light in the quiet heart of the Milky Way, where ordinary matter collapses into extraordinary silence. Sagittarius awaits. To most astronomers, it is the expected outcome of stellar death and galactic growth. A black hole, immense and invisible. Yet for others, its stillness conceals possibilities far stranger, ideas that hover at the edge of science, flickering between mathematics and imagination. These theories do not deny its weight or its influence, but they ask a haunting question. What if Sagittarius A is not what it seems? What if, in its darkness, it hides something altogether different? Some physicists suggest that what appears to be a black hole could instead be a wormhole, a mouth not to emptiness but to elsewhere, a tunnel through space-time, leading perhaps to another galaxy or even another universe entirely. The equations of general relativity allow for such bridges, though fragile and unstable. In this speculative light, Sagittarius A becomes not a grave, but a gate, a cosmic threshold through which matter and energy might slip into realms forever hidden from us. If true, then the stars that whirl around its core, like fireflies, caught in orbit, may not be circling a prison of annihilation, but a passage to something infinitely more vast. The Milky Way itself would be tethered to a beyond it cannot see. Others propose stranger forms still, dark stars or boson stars, exotic objects born not of ordinary matter but of hypothetical particles that obey rules unlike those of protons and electrons. These stars would be immense clouds of ultralight bosons, bound not by nuclear fire but by quantum coherence on galactic scales. From afar, they might mimic a black hole perfectly, bending light and sculpting orbits just as Sagittarius A does. Yet at their core, no singularity would exist. Instead, there would be a diffuse, ghostly structure, a shadow star whose heart never truly collapses. If boson stars exist, then Sagittarius A could be the first cosmic giant built not of matter, as we know it, but of something that whispers of new physics waiting to be uncovered. The holographic principle deepens the mystery. Born from the mathematics of black hole thermodynamics, it suggests that a black hole's surface, its event horizon, encodes all the information that ever fell within it. To many theorists, this is not just a curiosity, but a revelation, that the fabric of reality itself may be holographic. If true, then Sagittarius A does more than consume matter and light. It records, in the geometry of its horizon, the memory of everything it has touched: stars, gas, even radiation itself. The black hole becomes a library written in a language we do not yet know how to read, and perhaps, by studying its surface, we could glimpse the rules by which reality itself is built, where space, time, and information are woven together into a single, indivisible cloth. Quantum theory complicates the picture further. The paradox of information, the question of whether what falls into a black hole is lost forever or somehow preserved, remains one of the deepest puzzles in physics. Some propose that black holes radiate faintly, as Stephen Hawking predicted, slowly evaporating over unimaginable timescales. But if they do, then where does the information go? Is it destroyed, violating the sacred laws of quantum mechanics? Or is it encoded somehow in the radiation itself? Stranger still, some theories suggest firewalls, searing walls of energy at the event horizon, annihilating anything that dares to cross. Others resist this vision, insisting the horizon must remain smooth. In this debate lies a glimpse of something more than astrophysics. It is a collision between two great theories, relativity and quantum mechanics, and Sagittarius A sits at the center of this conflict, a silent judge awaiting resolution. The principle of cosmic censorship offers yet another layer of mystery. According to general relativity, singularities, those infinitely dense points where equations collapse, must always remain hidden within event horizons, cloaked from view. But what if this rule fails? Could Sagittarius A reveal not only the horizon but the singularity itself, exposed in naked form to the wider universe? If such an object existed, it would defy the very foundations of space-time, allowing us to peer directly into the abyss where all known physics unravels. Some believe this cannot happen, that the universe enforces its own censorship. Others wonder if the galactic center hides precisely such a forbidden truth. Speculation stretches even further. Perhaps Sagittarius A is not a tomb but a womb, not the end of matter, but a place where new universes bud from collapse. Some cosmological models imagine black holes as seeds of creation, each one giving birth to a new cosmos on the far side of the singularity. If so, then the Milky Way's central darkness may harbor more than an ending. It may shelter a beginning, a place where the laws of physics fracture and reform into new worlds. In this poetic light, the galaxy itself becomes apparent, its central black hole a hidden act of creation. What, then, is Sagittarius A? A prison of light, a library of information, a gate to the multiverse, or a womb of new beginnings? Each possibility bends the mind, yet all remain bound by the same observation. Something immense lies at the center of the Milky Way, shaping the destiny of stars and the order of the galaxy itself. Whether it is singularity, boson star, wormhole, or something beyond imagination, it is the great mirror of our ignorance, reflecting both the limits of science and the endless scope of human wonder. The notion of Sagittarius A as a wormhole carries with it both beauty and terror. Einstein and Rosen first described such tunnels in the 1930s, mathematical shortcuts through space-time that might, in theory, connect to distant regions of the universe. Later physicists extended the idea into speculative bridges to parallel realities, universes with laws of physics subtly or profoundly different from our own. The mathematics suggests that wormholes could exist, but nature may conspire against their stability. Without exotic matter to hold their throats open, such tunnels would collapse in an instant. Yet, if Sagittarius A were one such passage, then the matter swirling into its event horizon might not vanish into nothingness, but instead slip across a cosmic threshold into a region beyond our sight. To the stars orbiting nearby, the distinction would be invisible, the gravitational grip would be the same. But to the universe, it would mean that the center of our galaxy is not a place of endings, but of connections, tying the Milky Way to something unimaginably vast. The boson star hypothesis takes the imagination in a different direction. While wormholes speak of hidden bridges, boson stars speak of hidden matter, invisible, ghostly, yet immense. Bosons are particles that, unlike fermions, do not resist occupying the same state. Photons are bosons, and so are the hypothetical ixions that many physicists suspect may make up dark matter. If vast numbers of such ultralight bosons collapsed together, they could form a massive, diffuse object with gravity strong enough to mimic a black hole. Sagittarius A, from this perspective, would not conceal a singularity but a smooth, quantum-bound field. Unlike a black hole, it would not destroy information at its core, but cradle it within a strange, extended structure. Such an idea, while speculative, resonates with the broader search for dark matter, the unseen mass that shapes galaxies and holds the cosmos together. If boson stars exist, then perhaps the very heart of the Milky Way is the first evidence of dark matter in its most extraordinary form, a star not made of atoms, but of the hidden scaffolding of the universe itself. Layered upon these exotic models is the holographic principle, an idea born not from observation, but from the paradoxes that black holes provoke. Jacob Bekenstein and Stephen Hawking discovered that the entropy of a black hole is not proportional to its volume, but to the area of its surface, its event horizon. This strange realization suggested that a black hole's surface might encode every detail of what has ever fallen inside, like a cosmic ledger etched on a boundary we cannot cross. From this insight grew the profound suggestion that reality itself may be holographic, that our three-dimensional universe may be a projection from a deeper two-dimensional fabric. If this is true, then Sagittarius A is not merely an astrophysical object, but a clue to the very architecture of reality. Its horizon, dark yet radiant with meaning, could be a kind of cosmic archive, a place where the memory of stars and gas persists long after their fall. It is a library whose shelves are woven not of paper or stone, but of space-time itself. The questions of quantum physics deepen this enigma further still. Hawking radiation, if real, means that black holes are not eternal. They leak faint streams of energy evaporating over eons, until, eventually, they vanish. Yet in this process lies the infamous information paradox. Does the quantum record of what fell inside disappear as well? If so, the laws of quantum mechanics would be broken. To resolve this, some physicists propose that information is smeared along the event horizon, woven into the fabric of space-time in ways we cannot yet decipher. Others argue for firewalls, fierce walls of energy at the horizon, annihilating anything that dares to cross. If such firewalls exist, then the event horizon of Sagittarius A is not a smooth threshold but a violent boundary, a searing scar on space-time itself. This possibility shakes the foundations of physics, for it forces a choice. Either general relativity must bend, or quantum theory must. The galactic center becomes not only a physical mystery, but a battlefield for the deepest laws of the cosmos. And then there is the problem of cosmic censorship. According to general relativity, singularities must always be hidden, wrapped behind horizons that prevent their exposure. But if censorship fails, naked singularities could emerge, raw ruptures in space-time where infinity is exposed to the universe. Could Sagittarius A, under the right conditions, reveal such a core? No one knows. The stars orbiting close to it, like S2, trace paths that obey the predictions of relativity with remarkable precision. Yet physicists remain alert for even the smallest deviation, a whisper that something unusual lies within. If a naked singularity exists, it would not merely challenge relativity, it would overturn it, forcing a complete reimagining of space, time, and causality itself. The final speculation stretches the mind into cosmology. Perhaps black holes are not only endpoints but beginnings. Some models suggest that every singularity could seed a new universe, a budding cosmos unfolding on the far side of collapse. If so, Sagittarius A may not be a silent grave, but a hidden womb, nurturing the birth of new realities. In this vision, the Milky Way becomes a cosmic parent, its central darkness a secret act of creation, unseen yet essential. Our universe itself may have been born this way, from the death throes of another. If such a cycle exists, then Sagittarius A is both an end and a beginning, both tomb and cradle, its silence echoing with the possibility of worlds forever hidden from our sight. And so the galactic center remains a mirror to human thought, reflecting both the power of science and the boundlessness of imagination. Whether it is wormhole or boson star, holographic ledger or universe maker, Sagittarius A reveals as much about our ignorance as it does about the cosmos. It stands as the great enigma of the Milky Way, a silent reminder that the most familiar galaxy of all still holds secrets vast enough to humble the mind. In its darkness, science and wonder converge, reminding us that even in the age of observation, the universe still whispers of mysteries unmeasured, and of truths not yet born. At the dawn of the 21st century, humanity set its gaze upon the most elusive object in the Milky Way, determined not to let its silence be the final word. The center of the galaxy, long hidden by clouds of dust and time itself, began to yield its secrets as new tools of astronomy were forged. Foremost among them was the Event Horizon Telescope, not a single instrument, but a planet-sized network of observatories scattered across Earth, each one gazing into the night with unblinking precision. Through the technique of very long baseline interferometry, they stitched together their vision, creating the resolving power needed to peer into the very heart of darkness. In 2019, this grand experiment revealed the shadow of a black hole in the galaxy M87, a luminous ring of fire wrapped around a void. And in 2022, the same method captured the first direct glimpse of Sagittarius A, our own galactic center, its glowing plasma tracing the edge of the abyss. Yet the image, blurred by turbulence and time, was but the first step. Now, scientists refine the array, adding new observatories, expanding bandwidth, seeking to sharpen the cosmic photograph until the structure of space-time itself becomes visible at the edge of the horizon. Meanwhile, in the cold silence of space, the James Webb Space Telescope stretches its golden mirrors toward the galactic core. Shielded from the sun, cooled to the edge of absolute zero, Webb sees the universe in infrared light. The spectrum that pierces through the dense veils of interstellar dust. Where once the Milky Way's heart appeared opaque, Webb reveals its stars, its gas, its turbulent cradle of formation. Already it has traced the paths of young stars skimming the black hole's domain, measuring their orbits with exquisite precision. Each wobble, each flicker of starlight becomes a test of Einstein's theory, a search for the smallest cracks in the scaffolding of relativity. For it is here, closer than anywhere else, that gravity bends to its most extreme, where time itself stretches and warps in ways unseen by human senses. Alongside the direct gaze of telescopes, theorists weave simulations of staggering complexity. Supercomputers now model the dance of stars around Sagittarius A, predicting how their orbits shift under the pull of relativity and the unseen hand of dark matter. These digital galaxies, vast and intricate, allow physicists to compare prediction with observation, hunting for any discord that might reveal new laws of nature. Even the hot plasma circling the black hole is recreated in these simulations, its turbulence mapped with equations that merge magnetism, gravity, and light. To watch such models evolve is to glimpse, in artificial form, the living heartbeat of the galactic core. But vision alone is no longer enough. Modern astronomy has become multi-messenger, listening to the universe, not just in light, but in the faint echoes of other forces. X-ray observatories in orbit trace the violent flares erupting from Sagittarius A, brief flashes when matter plunges too close and is torn apart. Radio telescopes catch the whisper of jets and outflows that breathe energy into surrounding space. Deep beneath Earth's crust, Neutrino detectors wait for particles ghosting through matter, silent witnesses to the most violent cosmic collisions. And with the advent of gravitational wave astronomy, another sense has been opened: the ability to hear space-time itself ripple when massive bodies merge, though no such signal has yet been tied to Sagittarius A. The day may come when the galaxy's core speaks not in light, but in the vibrations of the cosmos itself. Future missions reach even further. Concepts for space-based interferometers envision telescopes in orbit, linked across thousands of kilometers, free from the distortions of Earth's atmosphere. Such instruments could one day deliver images so sharp that the horizon of Sagittarius A would appear not as a blur, but as a defined silhouette, its structure revealed in detail. The European Space Agency's planned Laser Interferometer Space Antenna, or LISA, will open the universe to gravitational waves of lower frequencies, sensitive to the slow dance of supermassive black holes spiraling together. These visions stretch across decades, projects requiring patience as vast as the cosmos they seek to understand. And woven through it all is the human story, a global collaboration of astronomers, physicists, engineers, and dreamers. No single nation could claim the center of the galaxy for itself. Only by linking observatories across continents, only by sharing data and ideas, could humanity glimpse the black hole that anchors the Milky Way. Each image, each measurement, is not the triumph of one person or one institution, but of a species reaching beyond the limits of its vision. To study Sagittarius A is to embody patience on a cosmic scale. Decades of watching, calibrating, refining, knowing that the object of fascination changes slowly, like a mountain shifting under the erosion of time. In this effort lies something profoundly human. The black hole at the center of the Milky Way does not need us. It has existed for billions of years, silent and vast, shaping the galaxy without witness. Yet humanity has chosen to turn its eyes toward it, to build instruments that stretch the limits of knowledge, to ask questions that may never find simple answers. This pursuit is not only about understanding gravity or testing theories. It is about connection, a reminder that even in the face of the most alien and incomprehensible of cosmic structures, the human spirit insists on seeking, on listening, on turning darkness into meaning. At the Paranol Observatory in Chile, another instrument sharpens its vision on the heart of the Milky Way, known as gravity. It is mounted on the European Southern Observatory's Very Large Telescope Interferometer. By combining the light of multiple telescopes into one, it achieves an angular resolution far beyond what a single mirror could ever deliver. With this tool, astronomers have tracked the orbits of individual stars as they skim perilously close to Sagittarius A, whipping around the black hole at speeds that defy imagination. One such star, S2, has become a cosmic probe, as it passed within a mere 120 astronomical units of the black hole. Closer than Pluto is to the Sun, its motion bent precisely as Einstein's equations had foretold. The shift in its spectral lines revealed the stretching of time, the gravitational redshift, a direct fingerprint of relativity at work. Each pass of such stars offers a new test, pushing the boundary between the known and the unknown, revealing whether space-time bends only as Einstein described, or whether subtler forces remain hidden beneath the surface. Even as telescopes refine their gaze, the galaxy itself conspires to make the task daunting. Sagittarius A is not steady, not silent. It flickers, it flares. At unpredictable intervals, it releases bursts of energy, sudden eruptions of X-rays and infrared light that blaze for minutes before fading into the calm of deep space. The cause of these outbursts is not fully understood. Perhaps they are sparks from magnetic fields tangling and snapping in the plasma whirlpool. Perhaps they are the death cries of asteroids or comets torn apart as they stray too close. Whatever their source, they remind astronomers that the black hole's environment is restless, alive with forces that escape simple explanation. To capture these fleeting moments, observatories around the world must remain vigilant, ready to turn their gaze within seconds of a flare's rise. In this way, the search becomes not just about static images, but about catching the black hole in the act of creation and destruction. A cosmic performance that reveals itself only in brief flashes. The effort is not confined to light alone. As gravitational wave astronomy matures, scientists anticipate a new way of listening to the galactic core. When black holes collide, they send tremors through space-time itself, ripples that sweep across the universe at the speed of light. Ground-based detectors like LIGO and Virgo have already caught the fleeting echoes of stellar mass black holes merging in distant galaxies. But the slow, deep waves of supermassive black holes can only be heard in space. That is the promise of LISA, a constellation of satellites flying millions of kilometers apart, linked by laser beams more precise than any ruler humanity has ever built. With such an instrument, the quiet heartbeat of Sagittarius A may one day be heard, or at least the murmurs of its kin across the cosmos. These signals would reveal the choreography of giants, the dance of galaxies spiraling together, their hearts merging in silent cataclysm. To hear such music would be to sense the universe on its grandest scale, a symphony written in the geometry of spaced IME. Each new frontier of observation forces theorists to refine their questions. For decades, black holes were thought of as simple, described only by their mass, their spin, and their charge. But Sagittarius A defies simplicity. Its magnetic fields twist, its plasma dances in turbulence, its horizon shimmers with light bent almost into a circle. Even the act of imaging, it challenges human concepts of measurement. For the light that reaches our telescopes has been delayed, distorted, and scattered by gas and dust across tens of thousands of light years. To reconstruct the truth requires patience, algorithms, and imagination. Teams of scientists now employ machine learning to sift through the noise, teaching computers to rebuild the shadow of the black hole from blurred fragments. In this union of human curiosity and artificial intelligence, the universe begins to give up what was once impossible to see, and still, beneath all the equations and simulations, lies the quiet truth of scale. The black hole at the center of the Milky Way is 4 million times the mass of the Sun, yet in cosmic terms it is small. There exist black holes billions of times more massive, lurking in the hearts of distant quasars, devouring matter with a violence that lights up the universe. Compared to these, Sagittarius A is subdued, modest, feeding slowly, a silent anchor rather than a raging beacon. It is this very quietness that makes it a perfect laboratory, where titanic black holes in other galaxies blind observers with their brilliance. Sagittarius A allows us to watch with clarity, to measure with care, to study gravity where it rules most strongly. Yet to watch is not enough. To peer into the dark heart of the galaxy requires patience on a scale unfamiliar to daily life. Decades of monitoring have given scientists only a few full orbits of the fastest stars. To see the longer arcs may take centuries. To refine the images to the sharpness desired may take generations of engineers, building telescopes, yet unborn. In this sense, the study of Sagittarius A is not only a scientific endeavor, but also a cultural one. It forces humanity to think beyond immediate time, to plant seeds of inquiry whose fruit will be harvested by descendants. This kind of patience mirrors the black hole itself, which has waited in silence for billions of years. The contrast is profound. A human lifespan is but a flicker compared to the cosmic ages. Yet through collaboration, through the continuity of knowledge, humanity stretches its reach across time, making the galaxy itself a mirror of our persistence. At the center of the Milky Way lies a silence so profound that it bends the very structure of reality. Sagittarius A, black hole for million times the mass of the sun, sits, cloaked in darkness, invisible to the human eye, yet its presence shapes the galaxy itself. Stars orbit it like sparks drawn to an unseen flame, their paths etched not by choice but by inevitability. This gravitational anchor, this invisible force, is both guardian and executioner. Without it, the galaxy would unravel. Because of it, entire suns are eventually devoured. Here, in this paradox, lies a truth that reaches beyond science and into the realm of philosophy, creation and destruction, order and chaos, life and death, all born from the same heart of darkness. To gaze at Sagittarius A is to confront the essence of mystery. It is not merely an astronomical object, but a metaphor written across the night sky. For in its presence we glimpse the invisible structures that guide not only galaxies but human lives. Just as stars move in obedience to the pull of this unseen core, so too are human destinies, shaped by forces they cannot see, by time, by chance, by the gravity of memory and desire. The black hole becomes a mirror, reflecting the hidden scaffolding of existence itself. Long before telescopes gave clarity to the night sky, ancient cultures sensed that the galactic center held significance beyond the visible. To the Maya, the dark rift running through the Milky Way was a cosmic womb, a place of death and rebirth, where souls pass between worlds. To others, it was the underworld itself, the entrance to a realm of gods and spirits. Without knowing of black holes, they intuited what modern science now reveals, that the heart of the galaxy is not empty, but full of mystery, not a void, but a threshold. These ancient myths, painted in symbols and carved in stone, echo the same awe that now drives observatories to capture images of the event horizon. Different languages, different ages, yet the same impulse to seek meaning at the edge of darkness. The paradox deepens when the scale is understood. The Earth, with its oceans, its mountains, its fragile civilizations, orbits a star that itself orbits the galactic core. Humanity's entire history, from its first sparks of fire to its most advanced machines, has unfolded under the quiet dominion of this abyss. Every moment of joy, every war, every dream has played out in a galaxy bound by a singularity that none can escape. The realization is humbling, even unsettling, for it reveals that human stories are not written on an independent stage, but on one woven into the gravitational embrace of a cosmic abyss. The very fabric of the Milky Way is scripted by this dark heart, and thus humanity, knowingly or not, has always been part of its story. And yet, instead of recoiling from this abyss, humanity gazes toward it with relentless curiosity. There is something in the human spirit that resists turning away from what terrifies it. Instead, it leans forward, daring to ask questions, daring to imagine what lies beyond the veil. The same instinct that once led ancient eyes to weave myths around the galactic center now compels scientists to build vast instruments across mountaintops and deserts, linking them into global networks, waiting patiently for photons bent by the black hole to arrive. This curiosity is not accidental, it is essential. For in facing what is most mysterious, humanity finds not only knowledge, but also meaning. Sagittarius A thus becomes more than a black hole. It becomes a symbol of the human condition, the desire to reach toward what cannot be grasped, to understand what cannot be seen, to wrestle with the infinite even from the fragile vantage point of a small world. It is both a reminder of limitation and a spark of transcendence. For though no human will ever fall across its horizon, the mind, through imagination and science, can travel where the body cannot. And in that act of reaching, the species affirms its place in the cosmos not as masters, but as seekers, bound to the same mystery that governs stars in the end. The story of Sagittarius A is not only about physics or astronomy, but about perspective. To recognize that the galaxy turns around a dark heart is to recognize that human lives, to revolve around unseen forces, love, mortality, memory, time. The black hole is both cosmic fact and poetic truth, both danger and wonder. It whispers that endings and beginnings are not opposites but reflections, that destruction and creation are twined together in the same eternal cycle. And as humanity stares into its depths, it is not only the universe that is being studied, but also the soul that longs to understand it. And so, the presence of Sagittarius A becomes a meditation on duality itself. It is the devourer, yet it is also the preserver, the very weight that keeps the Milky Way bound together. Without its gravitational anchor, the spiral arms would lose cohesion, and the great river of stars would scatter into intergalactic emptiness. It is destruction, written as creation, an engine of stability forged in collapse. This paradox sits at the core of the galaxy and the human imagination alike, that endings may in fact be foundations, and death may be a disguised form of birth. To contemplate this abyss is to wrestle with the same contradictions that have shaped religions, philosophies, and the private reflections of countless lives in the long arc of human thought. The idea of a cosmic heart, dark, hidden, and yet essential, has been a recurring image. Ancient myths spoke of sacred voids and unseen gods dwelling at the center of the heavens. The Mayan Xibalba B, the dark rift along the Milky Way, was imagined as the passageway between realms, a place of both origin and return. In Greek thought, the underworld was not far below the earth, but woven into the very order of existence, a hidden balance to the living world. These interpretations, though bound in the symbols of their cultures, mirror what modern physics now unveils, that the center is not an absence, but a presence beyond comprehension. Where the ancients saw wombs and underworlds, science sees horizons of no return, singularities of unimaginable density, and quantum mysteries that challenge the very logic of space and time. The humility this realization demands is profound. Earth, with all its complexity and beauty, is but a small pebble caught in the cosmic current. It circles the sun, which in turn drifts around the galactic center, its path one among billions, all tethered invisibly to Sagittarius A. Every human life, empires built, wars fought, poems written, discoveries made has unfolded under the dominion of this abyss, even though it remains unseen to the naked eye. The cosmic scale reduces even the grandest human story to a whisper, And yet, paradoxically, it elevates it as well. For the very act of understanding, of seeking to glimpse what lies beyond comprehension, is itself extraordinary. A species able to question its own place in such a vast order is already part of something greater than itself. Perhaps this is why Sagittarius A stirs both fear and fascination. To imagine a singularity is to imagine the breakdown of all known laws, the collapse of time, the annihilation of structure. It is a concept that denies the very frameworks the human mind depends upon. And yet, far from turning away, humanity directs its gaze toward it with almost devotional persistence. The radio dishes of the Event Horizon Telescope, the golden mirrors of the James Webb Space Telescope, the calculations running endlessly in supercomputers, all of these are modern expressions of the same impulse that once made ancient stargazers carve stories into stone. There is something almost mythic in this persistence, the drive to reach into the heart of darkness, to illuminate what should not be illuminated, to confront the abyss not with resignation but with wonder. Sagittarius A thus becomes more than a scientific target. It becomes a metaphor for curiosity itself. Just as no light can escape its horizon, no question posed to it can be fully answered. Every discovery deepens the mystery. Every explanation reveals new paradoxes. The black hole embodies the tension between knowledge and ignorance, reminding humanity that the cosmos will never yield all of its secrets, but it also affirms the value of the search. To strive for understanding, even when certainty is impossible, is what defines the human spirit. In this sense, the black hole is both an obstacle and an invitation. It asks, without words, whether humanity is willing to continue gazing into the unknown, even when the answers threaten to unmake the foundations of understanding. And perhaps this is where its true significance lies, not in the physics alone, but in the perspective it demands. For the black hole teaches that the universe is not built for human comprehension, yet it is still open to human inquiry. It reminds us that insignificance and significance are not opposites, but two sides of the same truth. The Earth is small, fragile, and transient, yet it belongs to a galaxy held together by a force so powerful that even light cannot escape it. To exist within that galaxy, to know of that force, to measure it, name it, and imagine its depths, is no small thing. It transforms insignificance into participation,